So welcome to this is the Further Math Support Programme online revision session for OCR Statistics 2. And what we're looking at in this session is sampling and the use of the central limit theorem, which again is quite pivotal in some other aspects in terms of hypothesis testing. So you need to be able to calculate and understand these things called unbiased estimators of the population parameters. Now we generally only deal with the mean and the variance here. So it's the understanding that we're using x bar to represent what we call mu hat, the unbiased estimator for the population parameter, and we're actually using s squared as the unbiased estimator for sigma squared, and we'll look at that a little bit later on. Also, you need to suggest improvements to sampling techniques. So sometimes some of the sampling techniques you're given are just not so very good, and you need to be able to improve them, and we'll look at the conditions of that. So you also need to be able to find the sample mean distribution x bar. So if you take lots of samples, your means will take lots of values, therefore it forms a distribution. And we either use the sample mean distribution when x is normally distributed, that's quite nice, and when it's not normally distributed, then we use the central limit theorem. And I've shown you an application of where the central limit theorem comes from in the hypothesis testing video. Otherwise there's too much for this one. Okay, so we're going to take, in this question, January 2010 question 1, we're going to take the values of 5 independent observations, and we're given this. So this is definitely a sample, okay? And we're asked to find unbiased estimates of the population mean and variance. So we're asked to find mu hat and sigma squared hat. They are the notations that we use for unbiased estimates. And you need to know that mu hat is effectively x bar, and you need to know that sigma hat squared is effectively s squared. And the way we define s squared is this big thing sxx that you saw in S1 divided by n minus 1 now instead of n. Sxx is equal to the sum of x squared minus the sum of x all squared over n. So that's the sort of tool set that we need to be able to tackle these questions. Okay, so let's start off by looking at the mean. So mu hat, and again, because we're specifically asked for unbiased estimates, it's a good idea to use the correct notation. If you put a hat on a parameter, it always means you're talking about the unbiased estimate. So in this case, mu hat is going to equal the sum of x over n, which is going to be 75.8 divided by 5, which gives me the grand total of 15.16. So you get one of your 3 marks from this. Okay, so for sigma hat squared, we need to be calculating sxx and then dividing it by n minus 1. So sxx is, in this case, 1154.58 minus the sum of x squared divided by n. Okay, so that doesn't change, that always stays the same. And if we calculate that, we're going to get 5.452. So sigma hat squared is going to equal 5.452 divided by 4. Okay, if you divide it by 5, you end up with what's called sigma squared, and we don't have a population, so we're not allowed to do that. So that's going to give me 1.363. Okay, so the way your method marks are awarded here is 1 is for using the formula, okay, effectively to find sxx. Another mark is for dividing by 4 in this particular case instead of 5, and you get an accuracy mark. Okay, now other ways of doing this is you could work out your variance in the normal way, so dividing it by 5 and then multiplying by 5/4, and it gives you the same answer. So that's what you might see on some mark schemes as well. Okay, so this is quite a nice question. And that is actually quite a nice way of doing this question as well. Okay, if you refer back, those of you doing S1 as well, if you refer back to the OCR S1 recordings, this is covered in detail there as well. So January 2010 question 2, so literally the next question. A college has 400 students and a journalist wants to carry out a survey about food preferences. She's going to take a sample of 30 pupils from the college using the following method. So she's going to get a list of all of the students. This, by the way, is called a sampling frame for reference. Number the students with the numbers running sequentially from 0 to 399. Okay, She's going to select 30 random integers in the range 000 to 999. If a random integer is in the range 0 to 399, then they're going to select that student. If it's greater than 399, then 400 is subtracted from the necessary until an answer in the range of 0 to 399 is selected. Okay, which seems a reasonably sensible thing to do, until you start thinking about it. Okay, so we've got to explain why it's not satisfactory. So here, we've got 000 to 999, so 000 to 999, and basically we're splitting this up into three categories. 0 to 399, we're then going from 400 to 799, and then we're going from 800 to 999. And the width here is 400 people, the width here is 400 people, the width here is only 200 people. So what that means is half of the people, so the first 200 people, actually have 3 opportunities of being selected. Okay, whereas the last 200 have only 2 opportunities. Okay, because we sort of run out of numbers. Okay, because there's only 200 in the last group. So basically this is not equally likely. So because each person is not equally likely, it's not random. Okay, so that's what we need to be aware of. Okay, so you get 2 marks for this. Basically you get 1 mark for saying that it's not likely. So B1 for not likely, not equally likely, sorry. And then you get another mark for your justification. Okay. How can it be improved? Well, quite simply, you just ignore these people here. So if you get a number that's above 800, 800 or above, you just ignore it. There's nothing wrong with doing that, okay? But what it does mean is you're using the numbers as effectively as you can, and everybody has an equal opportunity of being selected. So that's quite a nice question, and it's quite typical about getting you to think about how sampling techniques work. Okay, so January 2011, question 2. We've got a random variable h, and we're told that it has a distribution, and we're not told what mu is, which is fine. The mean of a sample of n observations is taken and is denoted by h bar. Okay, and we're told some information about h bar. Now we're told that this is normally distributed, so that's quite nice as well. So we know that if h is normally distributed, mu sigma squared, then I know that h bar, the mean distribution, is normally distributed mu 5 squared over n. Okay, because that's how h bar is done. So we've got 2 things we don't know. We don't know mu, we don't know n. So your brain should automatically start thinking in this context about a simultaneous equation. So we're given 2 statements about probability. Okay, so if you go to the normal distribution recording, I showed you how to find mu and sigma. One was by symmetry, and then I talked about solving them simultaneously to find mu and sigma instead. This is that example as well here. Okay, so basically we've got to work these through. So the probability of h bar being greater than 53.28 is given as 0.025. So I'm inclined to turn that around. So 53.28 being less than is actually equal to 0.9750, and we're also told that the probability of h bar being less than 51.65 is equal to 0.968. So because this is all to do with the normal distribution, we need to be using our normal distribution tables. Okay, so first of all, 9750, that's a lovely number, and it lives right here. So the corresponding z value is 1.96. So what that means is, if I look at the first statement, okay, and again don't forget I turned it round, we've now got the fact that we can standardize. So remind you of the formula, z is equal to x bar in this case minus mu over sigma over root n. Okay, if we're dealing with h being normally distributed like this. Okay, so standardizing this now gives me 1.960 is equal to 53.28 minus my mean over my sigma divided by root n. So that's the first bit dealt with, which is quite nice. We've then got to deal with the second aspect of this as well. Okay, so the other aspect is a little bit more difficult for two reasons. First of all, our probability is less than a half, so that is going to tell me that my z value would be negative to start off with. So what we do is we consider its complement, so that's 0.9032. And you can see that that's not in the probability table here, which is upsetting. So we have to go hunting in the normal distribution table, and here he is. Okay, so 0.9032 corresponds to a z value of 1.3. So this is going to correspond to a z value of minus 1.3. So standardizing here is going to give me minus 1.3 is equal to 51.65 minus mu divided by sigma over root n. So you can see we've actually got two equations now, equation 1 and equation 2, and we can then solve them simultaneously. So we've actually got 3 marks now. You get a method mark for setting up an equation correctly. You get your second mark for doing it twice, and then you get a B mark for making sure that both of your z values are correct. Okay, so now it's a question of solving these. So if we just tidy these up, we can see that we've got 1.96 root n, okay, just by multiplying that through, times 5 over root n must equal 53.28 minus mu, and here we've got minus 1.3 times by 5 over root n is going to give me 51.65 minus mu. Okay, so we've got some tidying up to do with, and the way we tidy it up, if we notice, we've got minus mu in each. So if I call this equation 1 and equation 2, what I'm going to do is I'm going to do equation 1 minus equation 2. And if I do that, okay, I'm going to get 16.3 over root n, okay, is equal to, I'm going to do that minus that, gives me 1.63. So I can see that this leads me nicely to state that 10 is equal to root n. Or in other words, n is actually equal to 100. So that's great. I found one of my variables. So now all I now need to do is to figure out what mu is. So we do that just by back substituting, and I can do it into any equation I wish. So I'm going to choose equation 1. So I'm going to have 9.8, that's 1.96 times by 5, divided by root n, which is 10, is equal to 53.28 minus mu. So in other words, mu is going to equal 53.28 minus 0.98, and that's going to leave me with a value of 52.3. And there's my value of mu. So for these 6 marks, just show you where all of your marks are now coming from. We've talked about the 3 marks for setting up your simultaneous equations in the first place. You then get a dependent method mark for showing some equation of finding root n. You then get from that an accuracy mark for getting the value of n completely, and then ultimately you only get a B mark for doing this. So that's quite nice, because it means even if you mess up the first bit, you're still going to pick up this mark here, which is really good. Okay, so this is quite a difficult question, but it does cover quite a lot of aspects of what you are required to do. Okay, so as I said, there is some ideas about the central limit theorem on the hypothesis testing recording I did. But again, practice these questions. Make sure you know how to improve sampling methods, because they do like asking those quite a lot.